Thanks a lot. Thank you, James. Thank you, all of you, for coming on a Saturday night. I'm sure you had nothing else to do on a Saturday night in London. So thank you for coming. I'd like to start by thanking the whole Royal Institution and Princeton University Press, everyone here from Dan to Rachel's to Stephen to James, Josh, and everybody. So thank you very much. I'm Claudia de Rham. I'm a professor of theoretical physics at Imperial College London, and there I study the secrets of gravity. So as you can see, I've done really good progress in the past few years because I found a secret to mysteries to float in midair, as you can see in the picture. But the reality is most of the time my own experience with gravity looks much more like this. And I can show that picture over and over again, and it's quite universal how people enjoy seeing me fall down, so that's good to see. But one of the secrets I'll share with you tonight is that deep down, I do think that gravity could have its own sense of humor. And it's a little bit like my own sense of humor. It may take a few billions of years for you to really appreciate it, so just be patient. Okay, so now that we have establish what it looks like or what it feels like to witness someone else experiencing gravity, let me ask you a slightly more personal question. What does gravity really feels like to you? And you may think of gravity as being associated to the pain you feel upon impact, upon a fall, but that in itself has got nothing to do with gravity. The pain you feel upon impact is related to the contact forces between solid objects, and particularly to the electromagnetic atomic bond within the cells of a body and that of the ground, and actually to Pauli's exclusion principle that prevents, for instance, two electrons from sharing the same state at the same time. And so the cells of a body and the atoms of the ground have to adapt for each other upon impact. That on itself has got nothing to do with gravity. So to really experience gravity much more truly, we should really extract ourselves from all the other forces, for all the other phenomena. And then somehow a lot of my friends often tell me that I should just go skydiving, ideally without a parachute. I don't know what they mean by that. So that I can really experience this feeling of freedom. But I'm not entirely free there. I'm not entirely in free fall, because of the friction of the air that still pushes against the front of my body. And I feel that. I feel this push, this pressure against the front of my body. On the rest of my body, and this is me actually going skydiving without a parachute, and I can tell you, you do feel that, particularly on the next day. But on the rest of your body, you don't feel anything at all, even though gravity is clearly acting on you. You're falling down. But you don't feel anything at all because gravity is acting on every cell of your body in exactly the same way. And so they're not pushed or torn apart. In fact, there's no single cell or taste bud in your body that can ever feel or taste or smell or hear gravity. If you're experiencing gravity in outer space, for instance, orbiting the Earth, you will be falling so freely that you don't feel anything at all. And yet, you're falling and you're experiencing gravity. But you're not feeling anything at all because every particle in every atom, in every molecule, in every cell of your body, as well as all the air in your spacesuit, is experiencing gravity in exactly the same way. There's something very universal. Actually, we call this the equivalence principle, which tells you that gravity acts on everything and everyone in the same way. And this equivalence principle was already postulated by Galileo at the end of the 16th century. And it was, for instance, one of the experiments that was first made to see, well, not the first one, but a visual way to see this equivalence principle was done during the Apollo mission on the moon by astronaut Mark Scott, as you can see here. Not because gravity is any different on the moon, but because there's no atmosphere, so there's no friction from the air. So when I hit play, you'll see that astronaut Mark Scott is going to drop on one hand a feather and on the other one a hammer, and hopefully, we'll see, they will hit the ground at exactly the same time, proving that gravity acts on those two objects in exactly the same way. He works. How about that? Galileo was correct. Yeah. This is the equivalence principle. So I spoke with the Royal Institution when I knew I was going to give a talk here, and we discussed about how to prove the equivalence principle here. And I said, well, really, we should all go on the moon and experience that. And then somehow they didn't want us to do that. So instead, thanks to Rachel, we have a really amazing experiment here, which is a tube. It's actually a tube, a normal tube. And Rachel has very nicely pumped all of the air out of this tube. And it's filled with some pieces of paper and a coin. Because there's no friction from the air, you can see that the paper and the coin fall in exactly the same rate. Even though their mass is clearly different, their shape, their color, anything else is clearly different. And yet, if you extract yourself from as many of the other external forces as you can, you see that these different masses experience gravity in exactly the same way. So this is what we call the equivalence principle, and it's really telling you that there's a level of universality in how we experience gravity and how we interact through gravity. And this is really what pushed Einstein to understand that there must be something much more fundamental about gravity. If everyone throughout the universe experiences gravity in the same way, and you can be something as heavy as a black hole or a hammer, not quite as heavy, or as light as a feather, or even as light itself, and you'll still be experiencing gravity, it means that there must be something quite deep in this way we understand gravity. It can't just be about two masses interacting with one another. It has to be encoded in something deeper than us. It has to be encoded in the very fabric of space and time. And now we understand, thanks to Einstein's theory of general relativity, that masses, like you and me, and the Earth and the Sun, curves the very structure of space-time around themselves, and that's how we're experiencing gravity. We all feel this space-time, we all feel this curvature. That's how we feel the gravitational attraction. The larger the mass and the bigger the curvature, the larger the gravitational pull. Now, throughout the universe, everyone is connected through this very fabric of space-time. So everyone and everything is connected through the gravitational attraction. We are connected through this gravitational attraction. Actually, the very notion of curvature, and hence the very notion of gravity, relies on connecting different points with one another. If you want to draw an analogy between the curvature of space-time with the curvature of a surface, it's easier for us to represent ourselves that. So you can think of the curvature of the surface of a roof, or this very beautiful surface here, which is curved. And we can tile this curved surface with tiles which are each one of them individually completely flat each one of them. And it is in connecting those flat tiles with one another that the curvature of the surface unfolds itself. And then in here, I've drawn a straight line connecting those tiles. It's a completely straight line. And when they are on this curved surface, this straight line may appear a little bit funny or curved. It is just the way a straight line looks like in a curved space-time, adapting for the curvature of the space or the space-time in which it's living. And that's why, for instance, the orbit of the planets around the sun may look like they're having some curved ellipses around the sun. But actually, these are just straight lines in the curved space-time. They're adapting for the curvature in which they live in. Now, for me, this experience is very tangible because throughout my life, I have been moving from one place to another, very conscious at every step on how to connect between these different points, from Switzerland to Peru to Madagascar to France to Indonesia to Canada to the UK to the US, back to the UK. And every time, as I left behind everything and everyone that made me who I was that far, it became clear that my entire existence, but also all of your entire existences, are nothing other than a patchwork of events in space and time. And it's up for me, up for all of us, to connect between them. In fact, there's never such a thing as a twisted life path in a straightforward world. Rather, we're all experiencing straight trajectories, adapting for the complexity for the world in which we're living. And throughout those journeys, the whole sky and nature at a more fundamental level is always there with us, a little bit like family. So whether we know it or not, and I know you do know it, but I think that's why we're all inhabited with a desire to understand nature at a more fundamental level. So let's do that. Let's understand the fundamental forces of nature. And let's start with the one we understand the best, the electric and magnetic forces. In this very theater, some 225 years ago, amazing, some of those experiments with electric and magnetism were done by Faraday himself. He's one of the first that realized that the electric and magnetic forces are not two disconnected phenomena. They're actually two different manifestations from the very same phenomenon. We know that the magnetic phenomenon has helped us as a civilization to travel the world for thousands of years. But that's actually nothing as compared to the impact that the electric force has had on hair fashion, as we all know. So this is something that we've done last week, because there's a small chance of having a heart attack when you do it. So I'll ask a volunteer to do that right here, right now first. No one? No one? We have a little volunteer here. We can always count on Barbie, so thank you, Barbie. She's going to show us how the force acts. And one thing, when I switch it on, there's a small chance that none of us will have a heart attack apart from Barbie, thankfully. There's a small chance that everything will go dark. This is to show that without the electric force, gravity wins. But as I'll switch on, you'll see that the electric force is so much stronger than the force of gravity. You have to apologize. You have to say sorry to Barbie. She's a little bit burnt. That's because she's been on a fight with Oppenheimer earlier this week, and she won, so that's fine. There's an order in the world. So when I put it on, you'll see her hair will go up, and what I'd like you to see and to really realize is how just through the transfer of a few electrons in her hair, there is some electromagnetic repulsion that compensate the gravitational attraction from the Earth. And just realize how weak the gravitational force is. Just a few electrons on her hair can compensate the whole gravitational attraction from the Earth. This is remarkable. So let's see if it works. If we don't, just all go away. How about that? And we had a few screens switching off, and my audio is off as well. So this is to show the effect. One thing you can notice here is that there's sparks coming on. There are sparks of light. The sparks, we'll see if things go back on again or not. But it's intentional. It's to show you that related to a discharge of electricity, there's a production of light, because electric charges are being accelerated through this discharge of electricity. And actually, Faraday himself was one of the first ones to postulate a connection between light and some electromagnetic vibrations. Nowadays, we understand that when we accelerate electric charges, we produce an electromagnetic wave. This is just a very fancy way to say we produce light. Light is actually the messenger for the electromagnetic wave. The electron, they communicate of some sort their electromagnetic repulsion against each other through a messenger, which we can think of it as light. We know there's lightning when there's a quick discharge of electric field, for instance, during a storm. And we're using that in our everyday technology now, of course. We're using this in the bulbs, which rely on electron being accelerated back and forth to produce light. Or we rely on that for telecommunication in antennas, which is also acceleration of electrons that produce radio waves for telecommunication. Radio waves are nothing other than electromagnetic waves at a particular frequency. It's just light. We're using that in our everyday life. So why am I talking about all of this? Really, we are here to understand the secrets of gravity. And I said that gravity maybe is a manifestation of the curvature of space-time, maybe it's not a force. And you probably heard that a lot of times, that gravity is not a force. And yet I'm standing here and I'm talking about a force, electromagnetic force, because deep down, gravity is a force. Deep down, gravity, even though it is a manifestation of the curvature of space-time, it has hidden in it a force in itself. And it can be described in exactly the same way as the electromagnetic force. In the same way as when I take electric charges and accelerate them with one another, I produce some electromagnetic field, which are called light. Now, when I take masses, which is my analog to the electric charges for gravity, when I take masses and accelerate with respect to one another, I produce gravitational waves, which I personally like to call light. But that's not a simple, no, this is just me. Now, when I shake my hands like this, I do produce gravitational waves. Do you feel them? Don't say yes, please. The intensity of those gravitational waves when I do that is so small that we're never going to detect them, and ever again. To produce gravitational waves with sufficiently high intensity and magnitude to be observable, we need huge objects, very massive objects, and accelerated very close to one another. So thank you for not saying yes, whether you feel my gravitational pull. So for instance, two stars or two black holes about to merge. When they are about to merge, they produce gravitational waves, and those gravitational waves, once produced, they travel through space and time over millions of years to reach us here on Earth, and we can detect them through instruments which measure how space and time get distorted as gravitational waves pass through. So this instrument, we call them interferometer, and their role is to measure distortion in space in various directions. As gravitational waves pass through, we can recognize a signal, as you can probably see on the top left. You may recognize this signal. This is the first signal of gravitational waves ever observed here on Earth in September 2015. And the announcement of that was on February 11, 2016. On the day of the announcement, you could pick up any newspaper throughout the planet on any language that you want, and the headlines would read, "Einstein was right." And so you'd be forgiven for thinking that the detection of gravitational waves may have been about proving Einstein right. But that's never the case. We don't do science to prove someone right or wrong. We do science to discover something new. We do science to push the barriers of understanding. And according to Einstein's theory of general relativity himself, there's still much more to uncover. And that's because Einstein's theory of general relativity doesn't only predict gravitational waves and the Big Bang and black holes and so many other amazing things. Actually, the very best thing I would say that Einstein's theory of general relativity predicts is its own failure. And that's undoubtedly the best feature that a theory can ever have, because it not only tells you where you are and how to make predictions and compare them with observations, it also tells you where to look for new discoveries. Now, to understand why Einstein's theory of general relativity does indeed predict its own failure, it's useful to go back once again to the other fundamental forces of nature. And you may think of there being many different forces of nature, but many of the forces that we experience in our everyday life are more contact forces, which some of them are related to Pauli's exclusion principle, and some of them are related to much more fundamental forces of nature. Actually, in terms of fundamental forces of nature, there's only 4 of them that we know of so far. There's the electric and magnetic force put together as one, as electromagnetism. Then there's the weak force, which is responsible in some sense for the structure within the atoms. There is the strong force, which is responsible for the cohesion of the quarks within the protons and neutrons inside the nuclei of the atoms. And then there is the 4th one, is the gravitational force. And one thing remarkable about all of those fundamental forces of nature is that we think they can be unified into one theory of everything. We already know that the electric and magnetic forces are not disconnected, they are unified into one framework. And I'll mention later, the weak force can also be unified with electromagnetism into an electroweak theory. And we do believe that this continues and continues. If we go back to electromagnetism, while I described it as having a messenger, which is light, the electromagnetic wave, at a more fundamental level, light can be described, as I said, as a wave, but also as a fundamental particle which we call the photon. In practice, what this means is if I take light of a particular color or frequency and reduce its intensity as much as I can, I'll see that it's carried by finite, discrete quanta of energy, which we call the photon. There can be 1 photon, one amount of energy, or 2 photons, the double of energy, but never anything in between, no matter how much I try to adjust the intensity of light. In fact, individual photons can be emitted or absorbed when electrons change energy levels around the atoms. Now, the weak force is also a fundamental force and can be unified with the electromagnetic force into an electroweak theory. This is known thanks to the work of Glashow, Salam, and Weinberg. The weak force also has a carrier which transmits this weak force, which we call the W and the Z bosons. Those are also fundamental particles, which we can detect, absorb, and emit. The weak force is actually extremely important. We wouldn't be there without it. It's responsible for fusion. It has some medical applications. Some of you may have gone through a PET scan, which relies on this weak force, and on the W and the Z boson. But we may not be quite as familiar with this weak force because the weak force is weak. It's weak. It's very weak. At least there's one concept which is quite easy. It's weak here. And the reason it is weak is because the particles that carry it, the W and the Z bosons, are massive particles in the sense that they have a mass, which means that they're much harder to excite. And nowadays, we understand very well how the Higgs mechanism is responsible for giving a mass to the W and the Z boson. I'll explain what I mean by that. And is responsible for weakening the range of the weak force, making the weak force weak. Electromagnetism, we say, has an infinite reach. In principle, we can have 2 electric charges quite far away from one another, and technically they will still mediate a small electromagnetic force with one another. But for the weak force, we know that it has a finite range. It only operates on subatomic scales, and beyond that, it switches off. So on bigger scales, we don't experience it. We don't experience the weak force. And we understand how the Higgs mechanism is responsible for switching this weak force off on larger distances. Very sadly, I'm sure you all know that Peter Higgs passed away just this week. I'm very sorry about that. And I thought, as a nice gesture, I will add a picture of him when he came to visit our physics department a few years ago. And I think this is quite symbolic on showing how interactions between Higgs himself and people around him has an impact on people around him, because this is precisely how the Higgs mechanism works. In reality, many other people and scientists were included in the discovery of the Higgs mechanism itself, but I'll call it the Higgs mechanism for simplicity. Actually, Higgs mechanism has really allowed us to understand much more deeply what it means to have empty space. It tells us something very profound about our understanding of empty space. So to understand what we mean by empty space, we're going to take this room and we're going to create a perfect vacuum here. So in a second, I'm going to ask you to all leave, please. And please take all the furniture along with you. All the air in this room, take it along with you. I'm a theorist, so I can tell you, but I can't do it myself. And we're going to create the perfect vacuum. When you go out, close the door. And what we're going to do is make sure we shield the whole room with a few kilometers wide walls so that no energy, no light, no cosmic ray from the outside can enter the room. So we will have created the perfect vacuum in this room. We may well win the Nobel Prize for how beautiful a vacuum this is. And yet, this vacuum is never really empty. It's filled with a vacuum bath, which is quantum fluctuations from all of the particles that we know of, including that of the Higgs. I'll call this the vacuum bath or the Higgs bath. And we know the detection of the Higgs and the understanding of the Higgs mechanism is the proof that this Higgs bath has an effect on other particles. We understand that the Higgs mechanism works as its interactions with the other particles. Light or massless particles, like the photon, don't interact very much with this bath. And so they're not affected in the dynamics. More massive particles, like the W and the Z boson, interact very strongly with the bath, and they are affected in the range of the dynamics. This is how the Higgs mechanism works, and that's how this bath, the Higgs bath, weakens the range of the weak force, weakens the dynamics of the W and the Z boson. But now we know from the equivalence principle that everything is connected to gravity. So this Higgs bath, for instance, is not innocent. It should have an effect on gravity. So let's go back to gravity once again. So just like we described the electromagnetic phenomenon as a force which had a messenger being light, but at a more fundamental level, light is carried by a particle which we call the photon, all of this is true for gravity. Deep down, gravity is still a force, even though it can manifest itself through the curvature of space-time. And just like the messenger for gravity or gravitational waves, if we took gravitational waves, it's very hard to detect them, so we can't really just take them like that. But if we were able to take gravitational waves and reduce their intensity as much as we could, we would see that they are carried by finite discrete quanta of energy, which we call the graviton. According to Einstein's theory of general relativity, the graviton is a massless particle, like the photon. But we'll see that this is not necessarily the case. In principle, individual graviton could be emitted or absorbed when electrons change energy levels around the atoms. But the probability for this to happen is extremely weak. And observing this will be extremely hard because gravity, as we've seen, is the weakest force there is, which means that we interact very weakly with individual graviton. But we've seen one here. That's my graviton. That's been made by my student Alicia. And now that we have a new toy in town, the graviton, what we're going to do is to explore it and understand how it behaves. So I don't know about you, but at home, when we have a new toy, the first thing we do is we kick it and smash it and crush it to understand how it will behave. And so let's do that. And actually, this is exactly what has been done in any particle collider. In any particle collider, this is the one at the LHC, the Large Hadron Collider, at CERN in Geneva, and in this case, they take protons and they smash them together to see how they will respond. And when this happens, sometimes the particles decide to transform themselves into some other particles. Sometimes they decide to do very different things. When we scatter particles, the precise outcome for one specific process is never certain. However, the probability of every single possible outcome can be computed with extreme precision compared with our observations, and it matches perfectly. We understand extremely well how the laws of quantum probability match our understanding of particle physics and our observation and experiments. Now, I can try to do the same thing with gravity. Of course, I can't do it quite in practice, but as a thought experiment, I can ask myself, hypothetically, what would happen if I were to take, for instance, two gravitons and smash them together? And I can use our laws of quantum probability, and I can use Einstein's theory of general relativity to determine the probability of the outcome. And this probability of the outcome is very well understood, can be computed. It makes complete sense all the way up to the point where I'm trying to be too greedy and the energy transfer in the process reaches an upper limit, which we call the Planck scale. I'll indicate the Planck scale here as ample, M for the mass, Planck mass. This is a Planck energy scale. This energy scale is 15 orders of magnitude larger compared to what is currently being probed at the LHC. So that's 1,000,000 billion times larger than the energy scale being probed at the LHC. So we're still a long way off from that. We don't need to worry. But what this tells us is that there's an upper limit up to when I can use Einstein's theory of general relativity to make predictions. And beyond that, the theory itself tells us nonsense. It tells us we have more than 100% probability of something to happen. Sometimes we have a negative probability of something else to happen. This tells us that we can no longer use the theory itself to make predictions at those energy scales. Now, as a theorist, I'm used to trading notion of energy with that of mass. This is what the famous E equals mc squared law tells us. You've probably all seen it. It's the most famous equation in the whole universe, possibly. It tells you that a notion of energy sometimes can be in the form of mass, but also mass sometimes can want to transfer energy. So there's a notion of high energy can correspond to a notion of large mass. But as we've seen, a large mass leads to a large curvature. And so what this tells us is that there are regions in the universe where the curvature is so high that the energy scale associated with it is close to the Planck scale, and we can no longer use Einstein's theory of general relativity to describe what happens in those places. Now, in the solar system, the energy scale associated with the curvature is always very small, even if you get very close to the sun. So we are safe there. It's all fine. We can use Einstein's theory of general relativity to make predictions, compare with the outcome. Whew, that's okay. To reach a curvature related to an energy scale which is close to the Planck scale, we need very large masses confined to very small regions of space. For instance, a black hole. And black holes are not just fragments of our imaginations. Black holes are unavoidable, and they have been observed. On your left, observation from the Keck observatories has been tracking the motion of stars at the center of a galaxy for a period of over 18 years, and you can see that they all seem to orbit an invisible mass at the center of a galaxy, which in fact has all the characteristics of being a black hole. And on the right is zooming towards the very same region at the center of a galaxy, now with the Event Horizon Telescope that measure radial light. So these are fake color, light of a particular frequency coming from behind that very same mass at the center of a galaxy. And we see that light has been bended by that huge mass at the center of a galaxy, and this is completely consistent with how we would expect a black hole to bend light around itself. Now, if you were to find yourself at the center of a galaxy, as you would over the weekend, this is not what you would see. You probably wouldn't see anything. These are fake colors. But what you would experience would probably be quite dramatic. As you get closer and closer to what we call this event horizon of the black hole, the horizon of the black hole, the gravitational attraction will become so large that you could try to run away from it. You wouldn't be as fast as the speed of light, and you wouldn't be able to escape. And once you enter the black hole, enter this horizon, there's no escape whatsoever, even if you were able to travel as fast as the speed of light, no matter how much you're trying to rush yourself out. As you go towards the black hole, you'll be squeezed along the transverse direction and pulled along the radial direction to the point that there'll likely be not much left of you by the time you cross the horizon. The experience may be a tiny little bit painful. And one way or another, by the time you enter the horizon, you'll likely be a little bit dead. However, as you go, I'm sure you'll be very relieved with the knowledge that Einstein's theory of general relativity is completely valid there. This may not be a very safe place for us as human beings, but as a theoretical physicist, that's a perfectly safe territory. We're perfectly happy there. Gravity has been tested at those curvature scales and is perfectly fine. So we can use Einstein's theory of general relativity inside the black hole to predict what will happen, even though we can't really go there. One thing that would happen is that the notion of space and time would switch with one another. And so I can't really discuss about the distance to the center of the black hole. I should really talk about the time scale to the center of the black hole. The distance, if I were to say it like that, is 11 million kilometers. That's about 30 times the distance between the Earth and the Moon. And in time scales, that's about 40 seconds. This is for the black hole at the center of a galaxy. Einstein's theory of general relativity will tell you that as you enter the black hole, you get pulled inexorably towards the center of the black hole, which is located in your future, in time in your future. And as you get pulled towards the center of the black hole, the curvature increases and increases. It increases and increases all the way up to the point where it reaches, the energy associated with it reaches the Planck scale, by which point you can no longer use Einstein's theory of general relativity to trust what happens. So the beauty is that you can trust Einstein's theory of general relativity telling you that it will fail at that point. Precisely what happens there, and even if the notion of space and time makes sense, so even if the very question of what happens there, which precludes the notion of space and time in itself, makes sense, is unknown. All we know is that we need a better description for gravity and for the laws of nature to have a better appreciation of what happens there. Einstein's theory of general relativity has broken down, has failed us before you reach the center of the black hole. So this is our current understanding and description of gravity. We know that Einstein's theory of general relativity is an extremely good description, impeccable description, I would say, for the behavior of gravity on a huge variety of scales. It works well in the solar system, on a galaxy, on a cluster of galaxies, but there are regions, there does exist region in the universe where the curvature is so high that Einstein's theory of general relativity has broken down, and we need a better description to describe what happens in those regions of the universe. Precisely what it is, I don't know. I wish I could share that secret with you, but I don't know. It could be string theory, it could be quantum loop gravity, it could be causal set, it could be something yet entirely, I don't know. One of the challenges that we have at the moment is understanding how, with underlying framework which we don't know about. How can we make predictions for what we should observe today? This is very challenging, but this is some of the work that my collaborators and I, and a big part of the scientific community, are trying to do at the moment. However, what I'm even more interested in is to understand what happens at the other side of the spectrum. That's another secret of gravity I'd like to share with you today. So what I'd like to understand is, if gravity fails us on very high curvature scale, could it be that gravity also fails us on, or I should say Einstein's theory of general relativity also fails us on very small curvature scale? So to understand how to look at gravity in regions of the universe where the curvature is extremely small, what we should do is zoom to the largest possible scales in the universe. So we can zoom out of the solar system, zoom out of the galaxy, zoom out of a local cluster of galaxy, over distances that span over billions of kilometers. It would take us millions of light, it would take us millions of years to get there if we were traveling at the speed of light. What we see on those distances is that clusters of galaxies are distributed along filament of dark matter, which are represented here in blue, but these are just fake colors. We can't see dark matter because light doesn't interact with dark matter, so we wouldn't see that. This is just an animation. So if we were to look at this picture, we may be under the impression that most of the energy present in the universe is localized along this filament of dark matter and clusters of galaxies. Something else remarkable when we look at the universe on those scales is that we realize that the further away we look at an object, the faster it seems to be moving away from us. And that doesn't tell us that there's something very specific about us, that we're very smelly and everybody wants to run away from us. What it tells us is that the very structure of space is expanding, is being stretched apart. The universe is expanding. It is the very structure of space which is expanding. The universe is not expanding into anything. The universe itself is expanding in itself. Now, there's one thing we know about gravity, which is we're all connected to gravity, and it is a gravitational attraction, which means that if it's true that most of the energy present in the universe is present through these masses around dark matter and clusters of galaxies, we would expect them to exert a gravitational attraction on each other and slow this expansion of the universe down. Maybe there could come a point where the expansion of the universe has been slowed down so much that it will stop, and it will stop expanding, it will start contracting instead. This is possibly what we would have expected. At the very least, we would have expected the expansion to slow down. But when we look at the universe on even bigger scales, what we see is exactly the opposite. The expansion of the universe is going faster and faster. The universe is expanding at an accelerated speed. This acceleration of the expansion of the universe is one of the greatest puzzles of modern physics, and is contrary to what we would have expected if indeed most of the energy present in the universe was confined in the clusters of galaxies and filament of dark matter. So to see if that's really the case, what we can do is zoom into a completely empty region of the universe, far, far away from any clusters of galaxies, far away from any source of life, in the middle of what we call a cosmic void. Imagine how lonely you would be there. There'd be no one to talk to, no planet to land on. You wouldn't even have a black hole to dive into to get yourself entertained for a little bit. And yet you wouldn't be truly alone. Because even in the best vacuum, you're still filled with all of the quantum fluctuations from all of the particles that we know of from this vacuum bath, including that of the Higgs. And as we said, this should have an effect on gravity. But the effect that this vacuum bath has on gravity is very different as compared to the effect that you and me and planets and stars have on gravity. When we're thinking about the way a planet curves the structure of space-time around itself, this is something very localized. It's just around itself, it curves this fabric of space-time. But when we're talking about this vacuum bath, it's not something which is just localized at some time or at some position in the universe. It actually fills the whole space in the universe and has done so since the very beginning of time. For billions of years it's done so, and does that through the whole volume of the universe completely uniformly. So what it does is not curve space-time just locally at one point. What it does is push the boundaries of space-time. There's not such a thing as boundaries of space-time. It pushes space-time as much as it can in every direction. This vacuum bath actually leads to an accelerated expansion of the universe, which is actually exactly what we are observing. When Einstein came up with the theory of general relativity, he didn't know that the universe expansion was accelerating. Actually, he didn't even know that the universe was expanding. Also, he didn't know that there was such a thing as the fundamental particle leading to a vacuum bath, including that of the Higgs. But now that we know all of this, we can put those ingredients together, and we can look at the effect of the vacuum bath on general relativity, on gravity, and we see that it leads to an accelerated expansion of the universe, precisely as we observe. This is the good news. The bad news is that the expected rate of this acceleration, based on the amount of vacuum energy or the amount of vacuum bath that fills the whole of the universe, is way, way, way too large. And the error is not just a factor of 2 or a small computational error that I can put under the rug. The discrepancy is actually of 28 orders of magnitude. This is the biggest discrepancy, the biggest embarrassment in the whole history of science. And it's been known for a century. And this is such an embarrassment because on one hand, you have general relativity that has never betrayed us, that predicts everything we have observed, including gravitational waves and black holes, to an impeccable precision. And on the other hand, we have this vacuum bath coming from particle physics that has also never betrayed us. It's been detected the Higgs, and we have understood the standard model of particle physics to an incredible precision. Both of them have never betrayed us, and both of them correspond to the pillars of modern physics. And yet we put those two things together, and we get the biggest discrepancy in the whole history of science. So what went wrong? I don't know. I really don't know. Is it our understanding of this vacuum bath or how the fundamental particle affect this vacuum bath incorrect? Or is its effect on gravity on the larger scales of the universe incorrect? In fact, Einstein's theory of general relativity has never been probed on such large scales. So that's a possibility. Very few possibilities have been proposed. And the one I like to raise, and it's a crazy one, but I'm going to raise it anyways, is that maybe rather than needing to take all of this vacuum bath quite so seriously over the whole history of our universe, over billions of years, and over the whole volume of the universe, gravity doesn't need to be quite so serious after all. The possibility I like to raise is to say, hey, gravity, time to relax. In Einstein's theory of general relativity, the graviton, like the photon, is a massless particle, which means that it has an infinite range. What this means is that technically, two objects, like two galaxies, located on the other side of the universe from one another, that is located 10,000 million trillion kilometers away from one another, still exert a small gravitational attraction on each other. Even more remarkable, to understand the dynamics and the dynamics of the whole universe, we also need to account for all of the vacuum bath that fills the whole of the universe. But maybe this is just too much to ask. Could it be that the gravitational attraction that we share, you and me, I hope you can feel it, and that we share with the Earth, and with the Sun, and with the galaxy, and even with our local cluster of galaxy, is only present because we are sufficiently close to one another? Could it be that we don't share the same gravitational attraction with objects and with a vacuum bath located on the other side of the observable universe, some 10,000 million trillion kilometers away from us? In practice, what it would mean is that we would need to weaken the range of the gravitational force. I can have a demonstration here on how it looks like. I'm sure you've seen such a thing before, like a trampoline surface. You put a mass at the center and you see how it deforms the structure of this surface. This is more or less what we had at the beginning with a few caveats. What we like to do here is restrict the range of the gravitational force such that if you have a mass, it only affects some given neighborhood. And so two masses located very far away from one another, technically they would stop having the gravitational attraction on one another. More importantly, we now need to account for all of the vacuum bath of the Higgs and all of the other fundamental particles to account for the dynamics of the universe and this huge accelerated expansion of the universe. So what we need to do is understand how to restrict or weaken the range of the gravitational force. But that's easy. Nature has already told us how to do that. Nature has already told us that the weak force is weak because the Higgs mechanism has weakened the range of this force by giving a mass to the fundamental particles that carry this force, the W and the Z boson. So in making the W and the Z boson massive particle, we have restricted the range, the operation of the weak force. So in principle, all we need to do is the same thing for gravity. Either we need to restrict the range of gravity from a point of view of Newtonian force if you want, or at the more fundamental level, what we really need to do is understand how to give the graviton a mass. And this is an extremely natural question. It's so natural that even Newton himself contemplated this possibility at the level of weakening or limiting the range of the Newtonian gravitational force. And many other amazing scientists since then, including Laplace. And then when we understood that gravity could also be carried by a fundamental particle and that was related to Einstein's theory of general relativity, and we understood that limiting the range of gravity was really corresponding to giving a mass to the graviton, this has been explored by many different scientists in the past century, including by Pauli, who's one of the founders of quantum physics, including Salam, who's the same Salam responsible, one of the founder of the electroweak theory and one of the fathers of the standard model of particle physics. And many other amazing scientists since then have been exploring the possibility of thinking what it would mean to restrict the range of gravity or give the graviton a mass. But this possibility has always been entirely refuted. And not because it contradicts observations. Quite the opposite. It could help with observation of the accelerated expansion of the universe and reconciliate the amount of energy contained in the vacuum bath and its expected contribution on the accelerated expansion of the universe. Now, this possibility has always been entirely refuted because it was impossible to make it work theoretically. Looking at the literature for the past century, on the topic, this is what you would read. No way, inconsistent, impossible, instability, and what I love most of all is plagued by ghost. Now a ghost, this is a scientific terminology, this is not me inventing for once. A ghost is the most terrifying thing that you can ever imagine. A ghost is a particle with negative energy, which would make the whole universe and you and me and everything living in it, even the very structure of space and time, decay instantaneously. So clearly, if we have a theory of gravity with a limited range, or a theory of massive gravity, we need to find a way to get rid of this ghost or to trap it. And this is what has been made possible to these two incredible gentlemen, Gregory Gabadazzi and Andrew Tolley. In practice, the trap that we engineered looked much more like an Asian stare or a Penrose stare, where we trick the ghost to live in a constrained space from where it cannot exit and do no harm. This is symbolic. The real proof uses lots of mathematics, but the result is the same. And to my mind, that trick was pretty cute in itself, but we soon came to realize that having one mathematical bulletproof proof for the absence of this ghost and the consistency of the theory of massive gravity would be enough. But soon enough, we realized that was never sufficient to convince the rest of the scientific community. To be sure, science and mathematics in particular, doesn't lie. So if something is proven in one mathematical language, it has to be true. But even in science, there's lots of different scientific culture and different mathematical architectures and scientific arguments that people feel more or less comfortable with. So over the years, every time a new colleague had a different perspective, we were compelled to learn the language and translate a logic and arguments to their way of thinking. And we have to repeat this process years after years after years until there remain no unanswered question. A theory about massive gravity wasn't judged by a closed jury of 12 peers. It was judged by the whole multicultural scientific community. Overcoming that process, though, was never the aim. It was just the start of the journey, one which would finally allow us to test gravity, compete it with Einstein's theory of general relativity. So if the graviton could have a mass after all, what would be its value? It'd be tiny, 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 tiny. We wouldn't want this distance to be as small as the subatomic scale, like the weak force, for instance. That would be just silly. We need those distances to be very, very large, which means the mass of the graviton to be very, very weak. If we put the graviton in a normal particle scale, if we wouldn't measure anything. It would be lighter than all of the massive particles that we know of, including the neutrino. So instead, we need very precise instrument to measure the mass of the graviton. And gravitational waves interferometer may be able to play that role in the future, including the LISA space mission that will allow us to detect gravitational waves with very long wavelength, very small frequency. If you think of them as color, it would be going very much towards the red and beyond. For a specific event, on the top is the type of signal you could expect to have if the graviton had no mass. While at the bottom is the type of signal you would get if the graviton had a large, large mass. The effect is very much strengthened because we're dramatizing it. We're making it very large. You see that the signal appears more compressed because gravitational waves of different frequency or different color travel at different speed. So in future experiments, by comparing our expectations with actual observations, we should be able to put a constraint, an even better constraint, on how light or heavy, massive I should say, the graviton mass is. Whether the theory of massive gravity developed by my collaborators and I will survive the test and be relevant at all for nature is for future generations to tell. But the possibility is now open. For now, I just want to contemplate the fact that right now, in this room, it can be day or night, I don't even know, clear or cloudy, I don't know, but gravitational waves are reaching us from the depth of the universe. And with them, they carry the most precious and important messenger there is. Detecting them and understanding them will allow us to understand if and how we connect with objects on the other side of the universe some 10,000 million trillion kilometers away from us. They will allow us to understand whether the infinitely small fluctuations from all of the particles that we know can have an effect on the biggest scales of the universe, possibly dictating its acceleration. And to me, this is remarkable because gravity is the weakest force there is. While we have detected gravitational waves, we will never, ever detect a single graviton like that, not per se. But what fascinates me the most about her is that she perfectly illustrates how the most subtle and discrete and shy particle there is can, through nothing other than sheer persistence over the billions of years of existence of our universe and cohesion with a gazillions of friends, be the most important element in the whole universe. She's the one setting space and time alive, the one responsible for the whole evolution of the universe, the creation of a galaxy, the formation of a home, and will be the one ultimately determining our own fate, that of the whole universe and everything living in it. So I'll stop here. Thank you.